Example B wants us to convert y squared equals 4x into a polar equation, and I'm going to go ahead and substitute y for r sine of theta, and I'm going to substitute the x for r cosine of theta. And if we square the left-hand side, we get r squared times sine squared theta is equal to 4r cosine of theta. And just like in example A, we want to solve this for r, so I can divide both sides by r, assuming that r does not equal 0, and we get r sine squared theta is equal to 4 cosine of theta. And then I want to solve that for r, so I'm going to divide both sides by sine squared theta, so we get cosine of theta times 4 divided by sine squared theta. Now, you could leave your answer like this, or sometimes people don't like fractions, and there's a couple different other ways that we could write it. We could write it as 4 cosine of theta over sine of theta times 1 over sine of theta. And the reason that I wrote it like that is so then we can change it into 4 times cotangent of theta times cosecant of theta using the reciprocal identities. So you could either write it like that or like this. Either of these should be fine. Example C gives us the equation x equals 2. I would replace x with r cosine of theta, and that equals 2. Then if I want to get r by itself, I would divide both sides by cosine of theta, and we get r is equal to 2 over cosine of theta, or you could write that as 2 secant of theta. So either of those is fine for this example. All right, for example D, we have the equation x squared plus y squared equals 9. And we know from previously that the relationship holds that x squared plus y squared is equal to r squared. So this part we can substitute with r squared equals 9. And then if we take the square root of both sides, we end up getting r is equal to plus or minus 3. Example 6 wants to express the following equations in rectangular coordinates. So we have in example A, r equals 4 over 1 plus sine of theta. I am going to take 1 plus sine of theta and multiply that to both sides of the equation. And if I do that, the left-hand side of the equation would be r times 1 plus sine of theta, and the right-hand side would be 4. Now if I distribute the r, I get r plus r sine theta is equal to 4. Hopefully you recognize that r sine of theta is the same thing as y, so I can go ahead and make that substitution now. And if I subtract y on both sides, we get r is equal to 4 minus y. In order to be in rectangular coordinates, we cannot have r, and so from here, what I'm going to do is I'm going to square both sides of the equation so that we can eventually get rid of the r. So the left-hand side will be r squared, and if I square 4 minus y, I would need to FOIL that, and that's going to end up being 16 minus 8y plus y squared. And then r squared, hopefully you recognize that that is equal to x squared plus y squared, so I'm going to make that substitution there. And now what I can do is I can subtract y squared on both sides, and I will get x squared is equal to 16 minus 8y. And now I'm going to subtract 16 on both sides, and I get x squared minus 16 is equal to negative 8y. and then I can divide both sides by -8, and if I do that, I get y equals -1/8 x squared plus 2, and I'm going to leave my answer like that. And that concludes example A. In example B, we have r sine of theta is equal to 3r cosine of theta plus 2, and r sine of theta is equal to y, and r cosine of theta is equal to x. So if we make those substitutions, we get y equals 3x plus 2. And this is nice that it's already explicitly solved for y, so I'm just going to leave my equation looking like that. Here in example C, we have r equals 2 times 1 plus cosine of theta. I'm going to go ahead and multiply both sides of the equation by r. So I have r times r is equal to 2r times 1 plus cosine of theta. And that's going to give us r squared is equal to, I'm going to go ahead and distribute 2r to both of these terms. Okay, so now we have the equation r squared is equal to 2r plus 2r times cosine of theta, and I know that r squared is equal to x squared plus y squared, and I know that r cosine of theta is equal to x, so we can substitute that to get 2x here. And then the next thing that I'm going to do is I'm going to subtract 2x on both sides. So I get x squared plus y squared minus 2x is equal to 2r. And we need to get rid of that r somehow. And I'm going to utilize a trick that we used previously to get rid of the r. And I'm going to square both sides of the equation. And if I do that, I'm not going to square the left-hand side or expand it out just because it's going to get, quite long. So the right-hand side, if we square that, that simplifies to 4r squared. And now we can substitute that. So I have x squared plus y squared minus 2x quantity squared is equal to 4 times x squared plus y squared, like that. And in this equation, it's going to be very difficult to solve that explicitly for y. So I'm just going to leave my equation like that and let that be our final answer. In example D, we have tangent of theta is equal to 1, and one of the relationships that we haven't really used in example 6 so far, we know that tangent of theta is equal to y over x, and the right-hand side of the equation will remain 1, and then this one is not too complicated to solve for y, so I'm going to multiply both sides by x, and on the left side the x's will divide out, and we'll be left with the equation y equals x. And that is our Cartesian equation for example D, and that concludes example 6 overall.